Hello. So what I'd like to talk about today is a couple of things. First of all, I'd like to start to talk a little bit about multivariable functions. And hold on a minute. So for example, f of x and y, we have a function of x and y. So, another thing that I'm going to talk about today is how the change in a function relates to changes in its variables. So we were really thinking about here of how the change in f relates to the change in y and the change in x. And if it's just one variable, how the change in the function relates simply to the change in x. But I want to start by talking about how we can visualize a two variable function as a surface. So if I start by drawing a set of axes, so here I have an x, y, and z axis. So here it's the x-axis, y-axis, and I can call this z. Okay, so each point in the xy plane, so the xy plane is down here. I don't want to keep it red because I'm going to draw a surface above it. So each point in the xy plane, so in other words, each value of x and y has a value representing the function. So for example, if I have this particular x and this particular, so this would be, let's say this is like x1 and y1. Okay, so I have this value of x and y. If I think of what is f at that point, so f of x1, y1 would be up here somewhere. We could put that on the z-axis. So a lot of times we say that z equals f of x, y. And so if you linked up all the z's, all the points, you would get some kind of surface. I'm just trying to draw what that might look like here. So this is a point on the surface. And this is the point. This is f of x1, y1, or you could call it z1. So you could see that if you linked up all of these points that are the value of f for each of the values of x and y that are on the xy plane, and you link them all up together, you would have a surface above the xy plane. Well, it wouldn't always be above. What I'm illustrating here is a function that only has positive values. You could have the surface cutting through the xy plane and going to negative values as well, but that would make it a little harder to just for us to talk about it here. So, so anyway, this surface really represents that two variable function, and it would be very hard for us to picture anything more visually, right? Because we only have 3 dimensions. So the third dimension is for the function, and we've used up, all of 3 space, so we don't have any way to illustrate a 3-dimensional function. So you just have to say, oh, okay, whatever we learn here for 2-dimensional function, we can just extend it. All right. So, so I guess I would say that the surface contains all of these f of xy's. It is a set of f of xy's representing each points above each one of those values of xy. All right, let me shut up about that already because it's not making it clearer. So anyway, what I'd like to start to talk about here is what about the slope? So when we have a one-dimensional function, so here, let me just draw a typical, here's a parabola, right? So this is x, this is f of x, which we often call y, okay? You have a parabola like this. what is the slope? Well, we know from calculus that the slope is very variable, right? The slope at any point is the derivative. Okay, so we could say it's derivative of f of x with respect to x evaluated, let's say here. Let's say this is, well, let me pick a better one that isn't over here. This is x1, and this is the slope at x1. All right, so this would be the slope at x equals x1. Okay, you could write it like df dx at x1. So, and you know, of course, at this point and this point and all these different points, you're going to have a different value of this slope because it's not a line. So the slope is the, and by the way, what I've tried to draw here is the tangent line to the curve. So the slope is the derivative at any given point, and it's really the slope of the tangent. And these are all things that you learned in calculus. But what happens if you have two variables? So you have this surface here. So we really, if we're talking about the slope at this point, we really have a slope in the y direction, kind of like this, and a slope in the x direction. I'm not really sure what this curve is doing, but I have a better picture, right? Because I took one from a book. And here's the better picture here. So here's a nice picture. Okay, and you could see here, here's a nice green surface. Here's a point P on the surface. And now what happens if I cut the surface parallel or along the y-axis? Okay, so this is the y-axis going this direction. So if I cut it, the cut is right here. This blue line represents that cut. Okay, let me make it red, right? So here's the point P, and this blue line here, which I'm going to make red, this is the tangent to the surface along the y-axis. And guess what? The slope of that line is what we call the partial derivative of the function with respect to y, because what's changing in this direction is y. Okay, so instead of using a derivative, we call it a partial derivative of the function with respect to y, right? So this z is really f of x, y, okay? So we have slopes, like I said, in two directions, because look, you have another line over here. So if I go down to this picture, try to bring that one up. Bigger. Oops, can't do that. Oh, there we go. So now, instead of focusing on what happens when we cut the surface, excuse me, along the y-axis, what happens if we cut it along the x-axis? So here's the x-axis. So that means I'm cutting it this way, making this cut. Okay, and I'm sort of focusing on this part of it right here. And this is the tangent to the surface as we go along the x direction. So this is tangent to the surface along x direction, or parallel to the x-axis. And so the slope of this line is the partial derivative of the function with respect to x. And you'll notice that this point is So the value of x is a and the value of y is b. Those are the values where we've cut the axis. So this really would be the df dx at the point AB. Okay, and the same thing over there for df dy. So we call, like I said, we call these partial derivatives. This is a partial derivative of f with respect to x. Okay, so that's sort of a very sort of quickie illustration of what a function looks like, a two-variable function looks like, and how you can cut that surface representing that function in two different directions, and you end up with two different slopes. And when we talk about how the function changes as you change x and y, we need to use both of those slopes, because one of those slopes describes how the function changes as you change x, and one describes how the function changes as you change y. So like I said earlier, last class, and in PChem, we're often most interested in changes to functions, not so much in what the absolute values of those functions are. So in PChem, we care very deeply about changes in functions, in particular, like the Gibbs free energy, the enthalpy, even the entropy, okay, and other things. So the question is, if we have a function of x and y, how does the change in the function, relate to changes in x, which is delta x, and changes in y, delta y? So that's the question. So that's kind of where we're heading here. But I think that when you take calculus, even one variable calculus, calculus 1, you don't really think about how the change in a function relates to the change in x in the same way that we do in PChem. So I want to sort of first start with the one-dimensional question, or the one variable question. So if f is just a function of one variable, how does delta f relate to the change in x? So this is the first question that I want to get at. Okay, so I want to talk about this first, and to get even simpler, to look at the very simplest case. What is the simplest type of one variable function? And I would say that it is a linear function. Okay, so here's a picture of a linear function, just a line. So here we have, say, x1 and x2. Here we have, so this is y equals f of x. And so we could call this y1, or really it's f of x1. And here we have y2, which we could also call f of x2. Okay. So we're saying, how does the change in the function? So how does the change in f, this is the change in the function here, delta f or delta y. How does delta f or delta y, those are the same thing, relate to delta x, which is this here? Okay, well, we know that we have a slope, and we generally refer to the slope as m. But we know that that slope is the change in y over the change in x. But now here's the thing that's really special to the linear problem. And that is that this slope is constant for a line. So look at this. If I take the derivative at any one of these points, I'm going to get that same constant value. The derivative at any point is going to be the same as what I would measure for the change in y over the change in x. And I know that delta y, sorry, that, let's see, how am I going to put this? Yeah, the change in the function is the slope times the change in x. You know, this is really, you know, what you learn in high school. Delta y over delta x is the slope. And then if I just say m delta x is delta y, that's really what I've done here. It's not anything special. I've just called it delta f instead of delta y, but that's because y equals f of x. And the m here now, I'm just going to say, well, we know that's the constant value of the derivative. For a line, it's constant. So we know that we have this for a linear function. So here is exactly how the change in x relates to the change in f. It relates simply by the slope. So if you start here at x1, okay, and here's your value f of x1, and you want to find out what is this change in the function, well, the line basically takes you there. Go down the line to the value x2, and it gets you to this point here, which is indeed the y2 or f of x2, and it will exactly give you, you know, if you take the difference between these 2 points here, it'll give you the exact value of the change in the function. Okay, so that's what happens if it's linear. So, you know, I did the simple case of one variable, and then I did the simple case of a linear function. So we have to answer the what if question. What if the function is not linear? All right, so that's what we're going to get to next. Okay, so what if the function is not linear? I think I have a nice picture down here, but it's way down. So I'm going to move it. So here is a very nonlinear function. It's got a lot of nice curvature to it. So here's my nonlinear function. Bigger. All right. So now we have a situation where here the derivative is not constant. You know, the derivative is the slope of the tangent. And that is really constantly changing in this function. It changes as x changes. So as I go here, I have a very steep slope. Here it's pretty steep, and then it's getting less steep and less steep and less steep. So these tangent lines are changing all the time, and the slopes of those tangent lines are changing as well. So if I'm at x1, okay, and I use the slope at x1, so I take df dx at x is x1. So what if I use this slope? So in the linear case, all the slopes were the same. In the nonlinear case, that's not true. So what if I use a slope here? That means the slope of that red line there, that tangent line. If I use that and I try, like this was the equation we had for the linear situation. I could have written this. I probably should have written it as, let me actually write it as that. Hold on. Probably should have written it as delta f equals df dx delta x. It's the same thing. but that's another way of writing it. So here, delta F, what if I take that df dx at x1, evaluated at x1, and multiply that by the change in x? So I'm really using the same equation, but is this an equation? So that's my question. Can I do this? Is that equal? And the answer is no. And you could see it from this picture here. So if you start at x1, there you are, and here's your change in x. And you do like for the linear function, you could as you travel from x1 to x2, this slope tells you where your function is at x2. So if we travel along that tangent line to x2, we arrive at this value. This is the predicted value using the slope at x1, which is the red line slope. And you could see that what this does is it overshoots the actual f of x2, okay? Because this is f of x2 right here. And you could see that it's overshot by this pretty large amount. So this is the true delta f. This is the real delta f. And this is the delta f that's predicted using the slope at the point x1, which is what I'm using over here. So these are not equal. Okay, so you can clearly see from the graph that these are not equal here, okay? The delta f that you get using the slope at x1 does not give you the correct change in the function. So I guess my question is, what can be done to get a correct expression, to get an expression that works? And the answer is, what we can do is we can make this interval smaller. So like if I take this line here and move it down, just sort of move it so that it gets closer and closer. So I'm narrowing down this delta x. What would happen is that that red line, as we move that interval, that red line is going to do a better and better job of giving you the value of delta f. Okay, so as delta x gets smaller, the delta f value will become closer to correct. And actually, in the limit, as that delta x goes to 0, it will be exactly right. So that is the actual fact, that in the limit, as delta x goes to 0, this equation, delta f equals df dx at that x1, delta x becomes exact. And so we write this instead as the infinitesimal change in the function. We call this the differential of f, which is just an infinitesimal change in the function, is equal to the derivative of the function with respect to x times the infinitesimal change in the variable in x. And this works anywhere, right? I mean, it could work any part on this curve. You started at any of these x values, you could predict what the tiniest little change in the function would be as you go to an x that's extremely tinily close. It's infinitesimally close to it. So we end up with this expression. And, you know, when you think about it, I mean, look, you could say, oh, these dx's, they cancel, df equals df, but maybe you know what it means a little bit better now. That in order to find the change in a function, you need to know what the change in the variable is, and you need to multiply by the derivative with respect to that variable. And so how does this apply to a two-variable function? Well, when we have a two-variable function, we have to worry about changing both of those variables. So let's go back to our surface. Maybe I can copy and paste it, might be better than just. Maybe I'll cut, paste it up here. All right, here's our two-variable function. So what we need to do is we need to figure out what the change in each variable is, figure out what the slope is in each direction, and then take, this is like the slope, right? Take the slope multiplied by the change, the slope in a particular direction. Let's say the change in x, the slope as you go along the x direction, multiply that by the change in x. Do the same for y. So for example, here we are on the surface right here. Make this nice and big. No, that's not doing it. Oh, there we go. All right. So we take this point, and this is the point P. So now we say, okay, if we have a change in x, that means this is the direction of the x-axis. So we're going to move down here a little bit along the x-axis, and we're going to get a certain value. You can see the y value has changed a little bit. So we have delta f along the x-axis, you could say. And now we're going to go along the y-axis. So we're going to go this way to the right, but we have to follow the surface. And the surface has a slope that's given by this blue line here. So it's like we're going like this. And now we have a change in the function as you change y, okay? And so this delta fx is like the change in f as x changes. And the delta fy is the change in f as y changes, okay? So our delta f, we call the total change, would be the change with respect to x and the change with respect to y. But we have to use our differential thing, our df here, because that is exact, right? Remember, if we use we have to make these changes in the variables very small to make this equation work. So we have going to have df is the differential change in the x direction and the tiny change in the y direction. And this is the partial derivative of the function with respect to x. That partial derivative is the slope in the x direction. So the df dx would be the slope of this line. df dy would be the slope of this other line. Talked about that earlier. So I would have to add up the contributions of the change in x and the change in y, and each gets multiplied by the slope in that direction. Okay, so this equation here is very much analogous to the one-dimensional equation, this df dx dx. Okay, these are actual d's now because they're actual derivatives if you have just one variable, but we call them partial derivatives. We have partial f partial x and partial f partial y. So that's df dx and df dy. And you have to take, those are the slopes, and you have to multiply each by the change in the variable, and that will give you this change in the function here as you change that variable. And then you change the other variable, you have to add up the little portion from that as well. So this is an equation that we really use pretty often in this course. And I think I already told you that we can have the dg, if you have the Gibbs free energy as a function of pressure, temperature, say moles of A and moles of B, if you have a reaction like this, that the dg would be partial G, partial P, dP, plus partial G, partial T, dt, plus partial G, partial Na, dNa, and then the same, but for NB. Okay, and this is, you know, I hope I've demystified this equation for you a little bit. These are the slopes in the 4 different directions, because if you have a 4 variable function, that's like a surface in 5 space. Okay, where you have, like, instead of just x and y, you have p, t, na, and nb. You can't really visualize it, but you can make an extension of the surface in a 3-dimensional space. And each of these, like I said, are these partial derivatives. They are the direction of the change in the function in only the direction of the corresponding variable. That's why this dg dp dp, dg dt dt, dg dna dna, right? It's always going to be the derivative with respect to a given variable times the change in that variable. And a lot of times we call this the total differential. So it would be the total differential dg, or over here, I would call this the total differential df. Okay, and so I hope that this gives you a little bit of a clue when I bring out this type of equation. And I'm going to do some examples of calculating partial derivatives when we have a known function, and then sort of putting them together to find expressions for the change in the function. So let's see, let's go to the, well, let me do an example for you. Okay, so here's an example. So, and this is an example of partial differentiation. And then I guess I could go ahead and write the total differential as well. Supposing we have a function of x and y, which is 5x cubed y to the 5th. Okay. So first, I'm going to illustrate partial differentiation. Okay. Just want to check something. So partial differentiation. Okay, so what this is now is if I want the partial derivative of this function with respect to x, I hold y constant, because when you're doing a partial derivative, you're only changing one variable at a time. So hold y constant. And a lot of times what I like to do is put the constants first. So we know 5 is a constant, but if we're holding y constant, then y to the 5th is also constant. So I could write this as 5y to the 5th times x cubed. That's the same thing. And df dx, well, that's going to be the derivative of this function with respect to x. Well, these are constants. So df dx would be those constants times the derivative of the function. I'm using the chain rule here. And the derivative of x cubed is 3x squared. So the derivative of a constant times a function is the constant times the derivative of the function. So if I put this all together, it's 15 y to the 5th x squared, and that is df dx for this function. Okay, so how do I find df dy? Now I'm going to hold x constant. Okay, so I had that the function was f of xy equals 5x cubed y to the 5th. These are constants when we're taking the partial derivative with respect to y. So the derivative of a constant times the function is a constant times the derivative of this function, which is 5y to the 4th. So this is 25 x cubed y to the 4th. This is 15 x squared y to the 5th, just to put the x's first. So that's df dy. Okay. So if I wanted to write my total differential, df, that's just partial f, partial x, dx, plus partial f, partial y, dy. Partial f, partial x is 15x squared y to the 5th times dx. I don't need a parentheses really, but whatever. Plus 25x cubed y to the 4th, that's df dy times dy. Okay, how you would use this, I'm going to do an example of this. We'll see one later. That's how you would write that total differential. So just to do some more practice with calculus problems, let's see. It's further up. I hate when there's big gaps. All right, so here is a calculus problem, just a partial differentiation. So now let's say that we have f of xy is this crazy function here, x sine y plus y cosine x. So what would be df dx? So we will hold y constant. So so this function here, f of xy, x sine y. So if we're holding y constant, then sine y is a constant. If sine y is constant, then the derivative of this term is sine y times the derivative of x with respect to x, which is 1. For this term, we hold y constant. And here, this cosine x is a function of x, and the derivative of cosine x is minus the sine of x. We have to carry over that constant. Okay, so the derivative of a constant times a function is the constant times the derivative of the function. So this is the derivative of cosine x, negative sine x. Did I do that wrong? Yeah, no, I didn't. So this is df dx is sine y minus y sine x. Right, that's a derivative with respect to x. Now I have to take the derivative with respect to y. Again, our function is x sine y plus y cosine x. So term by term, the derivative with respect to y. Okay, this is a constant with respect to y. So the constant times the derivative of the function. The derivative of sine is cosine. Okay, that's the first term. And here I'm holding, don't forget, holding x constant. So cosine x is a constant. So here's my constant. The derivative of y with respect to y is 1. So that makes the partial derivative of f with respect to y, x cosine y plus cosine of x. And if I wanted to put this together and write the total differential, it would be sine y minus y sine x dx plus x cosine y plus cosine x dy. Okay. Let's go to the next calculus problem. Just gonna do it right here. All right. So df dx here. So I have x squared plus 3x over y. So if I'm differentiating with respect to x, I have to hold y constant. So if y, so this first one, the derivative of this term is 2x. The derivative of this, well, 1 over y is constant. So that's a constant. Now I have to take the derivative of 3x with respect to x. So I get 3. So df dx is 2x plus 3 over y. Okay, that's df dx. For df dy, well, actually, I'll put it on the next line. So I'm going to hold x constant. So I have x squared plus 3x over y. So the derivative of that first term doesn't depend on y, so it's 0. And now I have a constant 3x times whatever the derivative with respect to y of 1 over y. And the derivative of 1 over y with respect to y is minus 1 over y squared. How do I know that? I use the quotient rule. Actually, I memorized that the derivative of 1 over x is negative 1 over x squared, but you could use the quotient rule, which is that the derivative of a quotient is the denominator times the derivative of the numerator, which is 0, minus the numerator times the derivative of the denominator, which is 1, over the denominator squared. And so you could see that you're going to end up with negative 1 over y squared here. So that's the derivative with respect to y. And we had the derivative with respect to x. I'm not going to bother to write the total differential. It's not very meaningful here. But the next example is a good example from this course, right? Because at the beginning of this course, we start with very simple cases. And the simplest case of all is an ideal gas. And this is really this is really a way of writing the ideal gas law. Basically, it's just P. Remember, PV is nRT. So I'm just writing P is nRT over V. So you can view pressure as a function of volume and temperature, and actually moles as well. But what I'm doing here is doing it for, say, 1 mole, or for you know, let's not make it 1 mole. Let's just say that N is constant. And R is a constant, so it's always a constant. But let's say we're holding N constant. So P is a function of volume and temperature. Okay, so dP, dV, we're going to hold T constant. So if T is constant, then all 3 of these, N, R, T, are all constant. And again, we have the derivative of 1 over V with respect to V. So let's see, the derivative with respect to V of 1 over V. Okay, so that's nRT times minus 1 over V squared. So that's minus nRT over V squared as dP dV. And then we want to take dP dt, and So for differentiating with respect to t, all this is constant. So it's nr over p. These are constants times the derivative with respect to t of t, which is equal to 1. So dp dt is nr over p. Okay, so now I want to write the total differential dp. That's going to be dp dv dv partial p plus partial p. A lot of times I just say dp dt instead of partial p partial t. It's just quicker. All right, so now plugging in dp is minus nRT over v squared dv plus nr over p dt. Okay. So now if I knew the change in v and the change in t, and they were small amounts, I could plug in whatever these values are, and t and v squared, you know, and similarly for n and p here, and I could calculate the expected change in the pressure. Okay. And now I'm going to just talk about problem 4 here. This is from the calculus. All these are from the calculus problems. So number 4 is a special problem. Okay, if you didn't come to lecture and you're in class in fall of 2021, this is due on Wednesday, which will be September 15th. If this is some other year you're watching this, and that's not relevant. So what this problem does is it gives you a function of 2 variables. Okay. First thing it asks you to do is calculate the value of the function at a certain point, at a certain value of x and y. So really you're calculating f of 1, 2. Okay, at the value when x is 1 and y is 2. That's pretty easy to do. Then it wants you to compute the partial derivatives in the techniques that we've learned. This is very similar to the example function I did. Calculate the partial derivative with respect to x and with respect to y. So you're going to get the functional form of these. You know, much like how we have the functional form here as nRT over v squared, or minus nRT over v squared. Here you'll get whatever it is, and then you will evaluate those derivatives at this point. X equals 1 and y equals 2. Now, what this problem explores is what do you get? What do you calculate for the change in the function if you change x and y by a very tiny amount? And what this tiny amount is going to be 0.01 in this problem. So we're going to change x. It's going to go from 1 to 1.01. And y is going to go from 2 to 2.01. So this is like x, this is x1 going to x2 and y1 going to y2, with a very tiny increment, almost like an infinitesimal. Not quite though. So what you're going to do then is really be calculating kind of at delta f. These are not quite infinitesimals, but you've calculated these derivatives. You've calculated them at 1, 2, right? They're calculated at this value. So use the derivatives that you calculated. So these were calculated in B, okay? And you kind of come up with a change in the function. This is really the change in f, all right? And so in A, you calculated what the value of the function was at the first point. So if you take the f of 1, 2 and add to it the change in the function, so this is from A and this is from C, then you will get a value of f at 1.01, 2.01. or at least an estimate of this value. And you can also, since you know the function in this problem, unlike what will happen in PChem, a lot of times, you can actually evaluate this function at 1.01, 2.01. And the question is, do you get the same answer? And then I would like you to explain why you do or you don't get the same answer. Okay, so that's a special problem, like I said. Okay, good.